Hello and welcome to this comprehensive video series on data structures and algorithms, commonly known as DSA. In this video, we are going to dive into some of the core concepts of DSA, starting with arrays, bubble sort, selection sort, and more sorting algorithms. We'll then explore linked lists along with their types and operations. And finally, we'll cover two very important structures, stacks and queues. Whether you're just starting your journey with DSA or looking to deepen your understanding, this video will break down complex topics into simpler, easy-to-follow steps. I'll be walking you through each topic with live code examples, a line-by-line breakdown, and real-world use cases. Grab a notebook, follow along with the code, and let's embark on this exciting DSA journey together. Now, let's get started. DSA arrays. An array is a collection of items stored at contiguous memory locations. It allows us to store multiple values of the same type together. This makes arrays one of the simplest data structures, and they serve as the foundation for many advanced structures. Key operations for arrays include insertion, deletion, and traversal. Arrays are great for accessing elements by index quickly, but they have drawbacks like fixed size and inefficient insertions and deletions. Code explanation. R equals 3, 5, 7, 8. This initializes an array with 5 integer values. Print R0. This line prints the first element of the array, which is 3. Print R2. This line prints the third element of the array, which is 7. R.append 10. This appends the value 10 at the end of the array. R.remove 5. This removes the first occurrence of the value 5 from the array. For element in R, this begins a loop that iterates through each element in the array. Print element. This prints each element in the array during the loop. Why arrays? Arrays are used when you need constant time access to elements and know the number of elements in advance. They are used in various applications such as image processing, databases, and matrix operations in linear algebra. Bubble sort is one of the simplest sorting algorithms where adjacent elements are compared and swapped if they are in the wrong order. It repeatedly steps through the list, and the largest element bubbles up to the top. Bubble sort code explanation. Def bubble sort R. This defines the bubble sort function. N equals len R. This line stores the length of the array in N. For I in range N, this outer loop controls the number of passes needed. For J in range 0, Ni-1, the inner loop compares each adjacent pair of elements. If Rj plus 1, if the current element is greater than the next one, a swap occurs. Rj plus 1 equals Rj plus 1 Rj, the actual swapping of adjacent elements. Why bubble sort? Bubble sort is used when simplicity is preferred over performance. It works well for small data sets or for educational purposes, but it's inefficient for large data sets due to its OON time complexity. DSA selection sort. Selection sort is an algorithm that repeatedly selects the smallest element from the unsorted part of the array and swaps it with the first unsorted element. It's simple but not very efficient for large data sets. DSA selection sort code explanation. Def selection sort R. This defines the selection sort function. Pause for I in range len R. This loop iterates over each element in the array. Min index equals I. This stores the index of the smallest element found so far. For j in range I plus 1 len R, this inner loop checks every unsorted element. If rj error min index, this checks if the current element is smaller than the one at min index. Ri r mindex equals r mindex. This swaps the current element with the smallest found element. Why selection sort? Selection sort is useful when memory writes are a concern, as it performs fewer swaps than other simple sorting algorithms. However, it has a time complexity of O(n squared, making it inefficient for large datasets. Insertion sort is a simple sorting algorithm that builds the final sorted array one element at a time. It is efficient for small datasets and nearly sorted data. Insertion sort code explanation. Def insertion sort R. This defines the insertion sort function. Pause for I in range 1 len R. This loop starts from the second element as the first is already sorted. Key equals Ri. The key is the element that needs to be inserted in the sorted part of the array. While j equals 0 and key rj, this loop shifts larger elements to the right. rj plus 1 equals key. The key is placed in its correct position in the sorted part. Why insertion sort? Insertion sort is best for small or nearly sorted arrays, as its average and worst-case time complexity is O(n)4, but for small arrays, its simplicity can outperform more complex algorithms. DSA quicksort. Quicksort is a divide-and-conquer algorithm. It selects a pivot element and partitions the array such that all elements less than the pivot come before it, and all greater elements come after. It is highly efficient, with an average time complexity of O(n log n). DSA quicksort code explanation. Def quicksort R. This defines the quicksort function. If len R equal 1, this is the base case. If the array has one or no elements, it's already sorted. Pivot equal R len R2. The pivot is the middle element of the array. Left equals x for x in R if x pivot. This creates a sublist of elements smaller than the pivot. Middle equals x for x in R if x equals pivot. This sublist contains elements equal to the pivot, right? X for X in R if X pivot. This sublist contains elements greater than the pivot. Return quick sort left, middle plus quick sort right. This recursively sorts the left and right sublists. Why quicksort? Quicksort is widely used because of its O(n) log n average time complexity and its efficiency for large datasets. However, its worst-case time complexity is O(n) sword, which occurs when the pivot is poorly chosen. Counting sort is a non-comparative sorting algorithm that works by counting the occurrences of each unique element in the array. It works well for integers and has a time complexity of O(n) plus k, where k is the range of input. Code explanation. Def counting sort r. This defines the counting sort function. Max val equals max r. This finds the maximum value in the array. Count equals 0, max val plus 1. This initializes the count array to store the frequency of each number. For num in R, this loop counts the occurrences of each number in the array. Sorted r.extend count I. This reconstructs the sorted array using the count array. Why counting sort? Counting sort is efficient for sorting integers with a small range. It is often used in situations where space complexity isn't an issue, and the range of input is small compared to the number of elements. DSA Radix Sort. Radix Sort sorts numbers digit by digit, starting from the least significant digit. It uses a stable sorting algorithm like counting sort to sort the digits. The time complexity is O(n) plus k, where d is the number of digits and k is the range of each digit. Code explanation for Radix Sort. Def Radix Sort R. This function implements Radix Sort. Max val equals max r. This finds the maximum value in the array to determine how many digits the largest number has. Xp equals 1. This initializes xp to 1, which represents the least significant digit. We will increase it by powers of 10 for subsequent digits. While max val xp 0, this loop continues as long as the quotient of max val divided by xp is greater than 0. This ensures that all digits from least significant to most significant are processed. Counting sort for radix r xp. This calls the counting sort for radix function to sort the elements of r based on the current digit. Xpt equals 10. This moves to the next significant digit by multiplying xp by 10. Why we use Radix Sort? Radix Sort is especially useful when sorting numbers with many digits, such as large integers or data that can be represented as strings of digits, like phone numbers or account numbers. It has a time complexity of O(d)n plus k, where d is the number of digits in the largest number and k is the range of the digit values, 0 to 9 in this case. Radix Sort is efficient for large datasets where comparison-based sorting algorithms like quicksort or merge sort might not perform well.